Calculating an infinite geometric series. As mentioned earlier, the common ratio R of converging infinite geometric series must be smaller than 1 when these series are converging. Extending this reasoning to negative ratios, we include the part of numbers that is greater than -1. Therefore, the condition for a geometric series to be converging, we have the following shown on screen. From tutorial 12.2, it is known that in such series, for the sum of the first n terms, we have the following shown on screen. When the number of terms increases to infinity, the value of Rn points toward 0, we have the following shown on screen. Since a less than b, the more n increases, the more r, n decreases until it becomes 0 for n equals infinity. Therefore, the formula for the sum of all terms in such geometric series becomes, we have the following shown on screen. Therefore, we can write the formula for the infinite geometric series with a common ratio between - and 1. We have the following shown on screen. Let's prove the accuracy of this formula by calculating the results of the two infinite geometric series discussed. Thus, for the series discussed in theory, we have the following shown on screen. We have x1 is equal to 1 over 2 and r equals 1 over 2 as well. We have the following shown on screen. And so on. Recall the general term for a geometric progression, we have the following shown on screen. Therefore, using the formula for the sum of all terms in infinite geometric series yields, we have the following shown on screen. As for the series discussed in the example, we have x1 is equal to 1 over 4 and r equals 1 over 2. Therefore, applying the formula for the sum of all terms in an infinite geometric series yields, we have the following shown on screen. Both values are the same as those found through other methods. Recall the first was a geometrical method based on the figure. Therefore, now we have in our hands a powerful tool to calculate the sum of all terms in infinite converging geometric series. Example. Calculate the following sums, we have the following shown on screen. Solution. A. Not all the given sum represents an infinite geometric series, so we must isolate the series part from the rest. Thus, we write the following shown on screen. We can write the expression in brackets, we write the following shown on screen. It is evident that the part of the expression that represents an infinite converging geometric series has the first term x1 is equal to 1 over 3 and the common ratio r equals 1 over 4. Hence, applying the formula for the infinite converging geometric series yields, we write the following shown on screen. Therefore, for the value of the original sum, we write the following shown on screen. B. We use the same procedure as in A, to isolate the series part. Thus, we write the following shown on screen. We can write the expression in brackets, we have the following shown on screen. It is evident that the part of the expression that represents an infinite converging geometric series has the first term x1 is equal to 1 over 5 and the common ratio r equals 1 over 2. Hence, applying the formula for the infinite converging geometric series yields, we have the following shown on screen. Therefore, the value of the original expression is, we have the following shown on screen. That is all for lesson 12.4.3. To continue this tutorial, please watch 12.4.4, the comparison test of convergence. Thank you for watching. Make sure to like and subscribe to keep up to date with new videos. For more information, calculators, and tutorials, please visit www.icalculator.com.